Alright, we're back again. And this time I'm gonna show you how to encode Boolean logic with functions. Alright, so I've defined two functions here. One I've called true and the other one false. Let's look at the implementation. I've just said and I've just asserted that these functions are the same thing as true and false. But it's really a matter of encoding, and it really depends on the way that you want to look at it. So true here is just a curried function. So in other words, a function that returns another one. That takes two arguments. So it's lambda a and lambda b, and returning the left side a, and false. It's just going to be some function that returns the right side. It allows us to define these connectives, logical connectives later on, that allow us to combine and test whether or not these normal rules and laws that we know from normal logic actually hold true. And when I want to test out whether or not such expressions are the same, normally speaking, there is also a way to define actual sound theorem provers. But for our use case, because that is a little bit beyond the scope of this video, I'm just going to define a simple criterion for whether or not two functions are equal. I just want to test whether the left hand of my logical expression is the same as the right hand. And because we're only going to test whether or not the result evaluates to true or false, I'm just going to implement only two simple sanity checks here. So in the first case, I want to have the result of true to return the first argument, so here 0, and if I'm comparing it with false, I want it to evaluate to 1 here, so the right hand side. So I hope that this sanity check provides you enough confidence that these functions actually are the same. Let's say we wanted to define our operator AND, and I just defined it here for you, and this may seem a little bit unintuitive, but let's just go through it and check whether it makes sense for us that this is actually doing what it's supposed to be doing. What happens when I evaluate n of true and true? Well, I'm getting AND of true. I'm taking AND, so I have my expression here. So let's plop it in here and see what happens if we apply this to true. So we had our definition of true. Just gonna copy it over. And so there we go. As you can see, I got one argument on the right and one lambda on the left, so I can eliminate these two. I have to replace all of these instances of v with lambda a, lambda b returns a. So let's start with the left one. I can see that this is a function that takes two curried arguments, w and v, and it's going to return the left one. So in other words, if I apply true here to w and v, it should return w. So if I go here, it will just be the identity function. And now AND of true and true, well, it's just going to be true, and AND of true and false, it's just going to be false. Okay. Similarly, let's take a look at AND of false. So if I have AND of false, I'm going to be applying my definition of AND here to false, and we can apply the same logic for reducing. So we have to replace all instances of v with lambda a, lambda b returns b. So now let me take a look, and again I can start with the left one. This is a function that is passed and accepting two arguments, w and v, and I have to return the right one. So it's going to be returning v, and I can further reduce that to this whole expression because I was replacing v with that. So I'm just going to be returning false no matter the case. No matter what I put in here, it's always going to be returned false. So if I do true here, then it makes sense that this will just remove the lambda false too, and you can see that we have regained the expression for false. Now, the case of OR is very similar, so let's take a look at NOT. If we compute NOT of true, so we have to replace all instances of v in this expression with true. So I had this expression and this is going to be true. Well, again, true is going to return the left argument of the two arguments that I'm passing in. This will reduce to x. And now my new expression is the same as false, because it will always return the expression on the right. Similarly, if I look at the not of false, I'm going to replace v in this expression with false. V was going to return the part on the right of my two arguments that I passed in, so I can reduce this to just w, and now you can see that the new expression is equal to true. And again, if I run this here, you can see that there are no exceptions being raised. Okay, so let's define if. And the kind of syntax that I'm looking to define would be something like this. If some boolean value, well, then on the left hand side when true, and on the right hand side when false. I'm basically inferring it from the syntax that I wanna get at the end. So I know that my syntax at the end, in terms of the information that I need, I'm gonna have to use 3 arguments, because I need to define what happens when it's true, when it's false, and I need to pass something in to know whether or not it is true or false. Maybe let's just see what we want to happen when it's if true. So if true of when true and when false, it should evaluate to when true. And if of false of when true and when false should evaluate to when false. Okay, so let's see. We want to apply our boolean somehow to these two, and let's just get an hypothesis and say that it's just going to apply them after another. Well, in this case, if it's true, does it make sense what I've written here? So let's say I'm taking the true of when true, when false. Well, then it should certainly return the left side of my equation, and if it's going to be false, then it should return the right side. So these expressions are more or less equivalent. Can you see that? So let's give an example of how to use our new if statement. I've just defined a small function, am I on the roof here? When I'm on the roof, I don't think I want to jump. But when I'm not on the roof, I think it's okay to jump. So when I print the result of am I on the roof false, then it's going to say jump. But if I'm not on the roof, then it won't. I've just put boolean at the end here. So now I can say, well, am I on the roof? When it's the case, don't jump. Otherwise, it's fine to jump. So who said we needed the built-in Python connectives to do logic? All you need is functions. That's it, and see you the next time.